For the first question, we have a cyclohexane ring. We have a ketone functional group, so this would be cyclohexanone. And we have a methyl and an ethyl group at the 1,2 position on our cyclohexane ring. And then assessing the stereocenter, since we have 4 different things attached to it. For the ranking, this carbon with the double bond oxygen is going to be ranked first. This carbon part of the cyclohexane ring is going to be ranked second. And this carbon ethyl group is going to be ranked third. 4 is in front. So looking at their rotation, we have a counterclockwise rotation, but since 4 is in front, it is in our stereocenter. So for the name of this compound, we have R at the 2 position, but we only have 1, so we don't have to specify it. So R. And then we have a methyl and an ethyl. Ethyl comes before methyl, so R2, ethyl, 2, methyl, and a cyclohexane ring. So we take off the E and add an O and E for the ketone functional group, which is at the 1 position. So I'll go ahead and add in the 1, even though it's not required. 1 cyclohexanone. Alright, for the next compound, we have 1, 2, 3, 4, 5 carbons. This is carbon number 1, which has our aldehyde functional group. We're going to take off the E and add an Al. And this carbon right here is a stereocenter. We have a hydrogen in the back. And for the rankings attached to this carbon, we have carbon that's ranked first because we have a double bonded oxygen. That's ranked second, and that's ranked third. So this is an R stereocenter with 4 in the back. So this is 2 methyl, so R in front, 2 methyl, and pentanal. And again, we replaced the E and added Al. For the next question, we need to propose a mechanism for each of the following transformations, as well as predict the product. So I like to start with the mechanism first, so I get all my carbons in line and think about what's attaching to what. So once our propane group, our propane nucleophile, because we've added our Grignard reagent, attacks that carbon, that'll get us to an intermediate where now we still have our 3 carbons for our propane. Now we've added another carbon, so we've actually converted it from propane to butane, and that carbon is now that CO2, and one of those oxygens is a negative charge because we push the electrons up the oxygen. When we do that workup with H3O, H2, so with a positive charge, H3O plus, we can do a proton transfer and make our carboxylic acid functional group. So we have made butanoic acid from CO2 gas and our 1-bromopropane starting material once we add that Grignard reagent to it. For the next mechanism, we have our weaker reducing agent, NaBH4. We're going to do a workup with an acidic solution, H3O plus. So for this, we're going to do a nucleophilic attack on the carbonyl carbon. And specifically, we've picked this ketone functional group. Remember, there's a greater partial positive charge on the ketone functional group than there is here because there is electron donation potential from the other group attached to the carbonyl if we have a carboxylic acid, an ester, and especially an amide functional group. So NaBH4, again, only attacks the carbonyl carbon of a ketone or aldehyde functional group. So that gets us to our intermediate. Now we have oxygen with a negative charge on it, and we still have our carboxylic acid functional group. It's kind of tough to write this. If we're under these acidic conditions, most likely we're going to do some proton transfers. The carboxylate would be deprotonated. This would end up being protonated, and then our workup solvent is really to protonate our carboxylate anion. If I saw that, that'd be great. If I didn't, that's fine. I mean, this is what happens in the mechanism. If you wanted to show the proton transfer here, that's probably not great because we basically said NaBH4 does not act as a base. So the reaction would happen later. Anyway, getting back to formation of our final product, again, we worked that up with water, so we'll do a proton transfer, kick off the leaving group, and that will get us to our alcohol functional group, and we still have our carboxylic acid. For the next question, we've converted our ester functional group into an alcohol, but we've also added 2 carbons. So we've added 2 methyl groups to this carbon right here. So for this, adding our 2 carbons, the only way we really know how to do that at this point, if we're adding just an alkyl group, is the Grignard reagent. And it looks like we're adding 2 methyl groups. So in the first step, we would need to add 2 equivalents of CH3 MgBr. So that's our Grignard reagent, which can attack this, push those electrons up. The electrons can come back down, kick off our ester, which will get us to our next intermediate, which would be a ketone functional group with a methyl group right here. And then we can add 1 more equivalent to attack that, add another methyl group, put those electrons up, and then the second step, we need to add an acid to protonate that alkoxide to be the alcohol functional group that it is. So I think I'm just going to actually draw the mechanism for each of these so you can see what's happening here. So our methyl group is nucleophilic because we added our Grignard because we made it into a Grignard reagent. So after that step, we get to an oxygen with a negative charge on it. Now we've added a methyl group, and we still have our O-methyl group. We still have our ester functional group. If we have a good leaving group under basic conditions, that can leave. That'll get us to our ketone functional group. Our ketone functional group is still reactive with the Grignard reagent. So again, our CH3 MgBr can attack that carbonyl carbon, push those electrons up, and that'll get us to our intermediate, which is our oxygen with their negative charge. We have a methyl group. We added another methyl group. Actually, the arrow should really come from here. That bond or negative charge on the carbon. Like I said, we have another methyl group there, and now we need to do a proton transfer, which are with our H3O+. So we can get to our final product. Alright, for the next one, it looks like we have a 5-carbon chain. I see a 5-carbon chain right here. We had a ketone functional group. We converted that into an acetal. So we switched from our ketone to our acetal. So in this case, we need, it looks like our oxygens that we added are connected via 2 carbons. So we need OH, and we need an acid catalyst. So if you put HCl or any acid catalyst, that's fine for that. So these are the reagents we need for the conversion. This is a 7-step mechanism. So if you wanted to practice this, I don't think I'm going to draw this one out, but if you wanted to practice, we do proton transfer. So for the proton transfer, we're going to protonate our ketone functional group, making our carbonyl carbon more reactive. That'll allow us to then do a nucleophilic attack. So one of our oxygens can attack our carbonyl carbon. And then we do a proton transfer. We would deprotonate that oxygen that just attacked that carbonyl carbon. And that would get us to our hemiacetal. Once we're at the hemiacetal, we do another proton transfer to make our leaving group a better leaving group. Specifically, that leaving group is the alcohol functional group. Once we make that leaving group a better leaving group, we can kick off that leaving group. So water would leave. Once water leaves, we can do a nucleophilic attack. Our other alcohol functional group would attack our carbonyl carbon, and then one final proton transfer would get us to our final product. All right, this one's interesting. So it looks like we have a ketone functional group here, and now we just have an oxygen, which we just made an ether. So in this case, I know that in order to make this a single bond, put a negative charge on the oxygen, the intermediate for the reduction reaction with NaBH4 will get us to this intermediate, where we added another hydrogen to that oxygen. And then usually we do a workup to protonate that into alcohol. But in this case, it looks like we added an ethyl group. So in the second step, we need to add an ethyl group with a good leaving group on it. So something like ethyl bromide, so we can do a nucleophilic attack on that carbon, kick off the leaving group, and that'll get us to this product. All right, for the next one, if we use our reducing agent LAH and work that up with water for amines, that means that this bond is not broken. So for amines, that means this bond is not broken because the carbon-nitrogen bond is pretty stable. There's pretty much equal sharing of electron density with the electrons in that bond. So what happens is we end up basically just fully reducing this carbon to be a CH2. So for our carbon chain then, now we just have NH2, and that is it. All right, for this is actually the exact same thing. It looks like we're putting our protecting group on a ketone, so we're actually going to end up with this product right here. I'm going to draw it a little bit different. So here we have our 5-carbon chain with our ketone, which was transformed into our acetal functional group. So that's the protecting group that we would put on our ketone functional group.